Hello, this is Brian Purdy with the Florida Aviation Network. Today at the 2023 National Business Aviation Air Association Convention in Las Vegas, we're meeting with Marc Ausman. He's the Chief Product Officer for Electra, and behind us is their model aircraft for the Electra. So we're going to talk a little bit about that and find out how it can be used, its propulsion, and go from there. Good morning, Marc. How are you doing?
Good morning, Brian.
Okay, great. I was telling you earlier, I managed to sit on your panel discussion, and I was quite impressed, and I understand exactly where you're coming from, and we don't want to get short-sighted and thinking one thing is the best thing as far as batteries. Yeah, well, okay. So we're going to talk a little bit about not only your aircraft, but how you see it being used and such like that. So I'll just let you go with it.
Yeah, happy to talk about that. And we met earlier on the panel, and what we were talking about was that there's no one aircraft that can do every mission, right? Certain aircraft are great for this mission, other aircraft are great for another mission. The mission we're focused on is that 50 to 500 mile regional air mobility mission, where you can fly people and cargo mainly between existing airports. The United States and other parts of the world have a lot of smaller airports that are underutilized, and they really are great because you can get an airplane like this into those smaller airports. And you can do it quietly, you can do it with sustainable fuels, and really address a lot of the issues that are prominent with today's traditional aircraft. And I was just going to say, what we're developing here is a 9-passenger hybrid electric aircraft. So think of it about the size of a Cessna Caravan, but it has some new unique features that gives it new and unique capabilities that no existing aircraft today has.
Okay, great. And I remember some of the things you talked about, a 300-foot takeoff,
right.
And that's possible because of your blown lift, the distributed propulsion and stuff. If you'd like to give us a little bit more specifics on that.
Right.
And,
so this aircraft will take off and land from a 300-foot runway. That's about the size of a soccer field or a football field. And it can do that because of this new technology called distributed electric propulsion. And if you look here, you can see these smaller propellers, and you can only see, I guess, 2 of them in the camera here, but there's 4 electric motors on each wing, 4 propellers, so a total of 8 electric motors driven by a hybrid electric system. And the way it works is the flaps come down, the ailerons actually droop, and the motors blow air across the full span of the wing. And that allows you to get a lot more lift at lower speeds. And so what this aircraft can do is it can fly approaches at 30 knots and cruise at 175 knots. And there's no aircraft in existence today that can really do that and do it in a commercially viable manner, meaning that an operator can carry passengers or carry cargo and make money off that aircraft.
Now, for other pilots, it's almost like, okay, we're flying in a high-performance short field, maybe even a soft field configuration for both takeoff and landing.
Well, it's really not as extreme as most STOL aircraft are. So typically, if you have a short takeoff and landing aircraft called a STOL aircraft, you sacrifice cruise performance. And you also, are flying an approach at a very slow speed, right at the edge of stall. It can be kind of dangerous. Very skilled piloting is needed. This aircraft really has a fly-by-wire system, and it manages that precise interaction between the flight control system and the electric motors to really be able to fly that approach safely. So you're not at a high pitch angle hanging on the props. You're actually flying at a very near level altitude at a fairly steep descent rate at about 30 knots and very well within control. And the way the blown lift technology works is that it blows air over the wings and then it is deflected downward by the flaps and ailerons. And so if you're flying an approach at 30 knots, the air is going over the wing at maybe 70 knots. And so that wing has substantially more lift than if it was not blown. And that means you can fly very safely at 30 knots. Normally, if you flew at 30 knots, you'd be just hanging in the sky and not a situation you want to be in. But in this case, it's very, very safe. And so when you land at 30 knots, it's very gentle. It's a very gentle deceleration. And same when you take off. When you take off, you're in the air within about 3 seconds. It's really pretty amazing. And you climb out. Feels very normal. There's nothing unusual about it. And then the speed will build up as the flaps come up. So it's not what you might think of as your grandfather's STOL aircraft. This blown lift technology really makes it a very normal takeoff and landing. And you can also operate it as a very conventional aircraft. So if you got a 7,000 foot runway, you've got a 4,000. If you got a 2,000 foot runway, just take off and land like a normal aircraft. Keep the flaps up and accelerate and take off that way. So you can do that as well.
Now, if you are taking off on a longer runway, does that gain you a little bit more range because you're using potentially less power?
You are using less power, but with a hybrid electric system, you have fuel that's being burned by a turbine. It's converting that into electricity, and that electricity powers the electric motors and also recharges any batteries that are used. And so the net difference is really insignificant. If it were a pure battery electric aircraft, it would be a meaningful difference. But with a hybrid electric, the difference isn't that much. And so you might be asking, well, why do you need a STOL aircraft if you're taking off from a regular runway? And you can take off just like a regular aircraft. But when you take off in a STOL configuration, you actually leave the runway more quickly, you climb out more quickly, and so by the time you're past the end of the runway, you're already over 1,000 feet, and the aircraft's much quieter and less disturbs the surrounding neighborhood.
Now, me just going off on a tangent here, but most people, they're thinking, okay, you need a certain amount of speed to take off.
Yeah.
But with the blown lift, which you're actually doing, because really it's the lift from the pressure differentiation between the upper and the lower, and since you're controlling how much airflow is going over there,
yes,
you're generating lift without necessarily requiring speed.
Correct. It's a combination of the pressure differential between the upper and lower part of the wing, as well as the deflection of the airflow downward, and that creates what's called a jet flap. And that jet flap actually means that the effect of the flap is much greater aerodynamically than it is physically. So the flap is about aerodynamically twice as big as it is physically. And that gives you more drag, gives you more lift, and that's what gets you up off the ground or allows you to approach more slowly than you would in a normal aircraft.
Now, I may get a little bit technical on here.
Yeah, that's okay.
I always get into details, problem being an engineer. So how much power is each electric motor using?
So on the production aircraft, each electric motor is 105 kilowatts, which is about 130 horsepower, times 8, right? So you have 840 kilowatts power to take off for takeoff.
And that's what you use to determine the size of your power generation that you'll need?
Right. Well, that's takeoff power. Cruise power is less. That's about 600 kilowatts. And so you have less power for cruise, more for takeoff. Now, the wonderful thing about electric motors that you can't do with pistons or turbines is you get a surge of power. So a piston, you get 0 basically. A turbine, you get maybe 10%. You can get 50% more power for a short period of time out of electric motors. So they're sized for cruise, but if, let's say, one of the motors fails, so let's do a little math here, right? So you got 8 times 105 is 840 kilowatts of power for takeoff. Well, if you lose a motor, the computers are going to shut down the other side motor as well.
Just like if you got multi-engine rating, okay, we got a feather and balance out.
You don't have to do identify, verify, feather. You don't have to do any of that stuff. What you do is you just keep flying. Computers handle all that automatically. So what happens is now you have 6 motors. Well, it takes the other 6 motors and it surges those to 140 kilowatts. So 6 times 140 is 840 kilowatts. So you still have 840 kilowatts, which is times roughly 20%. So you're looking at maybe 1,000 horsepower for takeoff, no matter if you have 6 motors or 8 motors. So you still have that 1,000 horsepower or 840 kilowatts that you need for takeoff. So very, very safe. Lots of redundancy. Unlike, say, a twin, you take off in a Baron, you lose an engine on takeoff, you get your hands full. In this plane, it's a complete non-event. Okay, great. And then, like I said, determining what your power generation device is, whether it's a battery or your hybrid generator, it's like an onboard generator, I think. Think of it as like a large APU that's optimized for power. APUs are really for ground operations, but this provides power throughout the entire flight envelope. And is that APU geared towards that maximum takeoff, or just, hey, we're going to have it even more powerful and that way it lasts longer if we don't have to use it all? No, the turbine is actually always operating at optimal performance, which means you get very long TBOs, you get very efficient fuel burn, and On takeoff, so the turbine is rated at about six, and these are all ballpark numbers for the sake of discussion, 600 kilowatts.
Okay.
And then you have a battery pack, which is part of the hybrid system. So on a Toyota Prius, you've got an internal combustion engine,
Mm-hmm.
you've got a battery pack, and you have electric motors.
Okay.
It's the same kind of general idea. It operates a little bit differently, and so you've got the 600 kilowatt turbo generator. But then you need another 240 kilowatts.
Mm-hmm.
Well, where does that come from? It comes from the battery pack. So it drains the battery pack by just a little bit. It's very gentle on the batteries for takeoff.
Mm-hmm.
And if you do lose the turbo generator on takeoff, the battery pack will continue to provide that energy and that power for the electric motors.
Mm-hmm.
So you have enough battery energy to fly around the pattern, come back and land again. So you actually have 4 independent battery packs plus a 5th source of power, which is the turbo generator, and you can lose multiple different sources of power and still be safe.
Okay.
So it's very, very safe.
I was already thinking of that. Okay, that battery is almost like your reserve.
It is.
Okay.
Yeah, but it's a necessary part of the operation to provide that extra power. Otherwise, we'd have to size the turbo generator for that full 840 kilowatts, which means it's bigger, it's heavier, more fuel burn and everything. So we can keep all the components smaller, and that's why a bunch of small components is actually better than one big component, which is the way things operate today.
I think that's what I was getting back. I didn't realize there was actually battery packs on board.
There are.
So
there are. They
that
provide safety and redundancy.
Okay, great. I'm truly impressed. And what size and what kind of customers are you looking to have?
So we have some pretty significant interest today for this aircraft. Our primary customer base consists of Part 135 operators who charter both passengers and cargo today. So there's a variety of traditional aircraft that they fly today, and this aircraft is designed to fit right in with the way they operate today. So they can take the old aircraft and plug this one right into their operations. It requires a standard pilot certificate, nothing unusual or special. Unlike some other electric aircraft, so we have about, at this point in time, about 1,600 aircraft on order through letters of intent, which is over about $6 billion in backlog for this aircraft, and that's mostly Part 135 operators. There's some corporate flight departments in there, and there's some other really exciting stuff coming down the horizon that I can't talk about right now, but really seeing a lot of interest in this, and it's because this aircraft is not a science project. This aircraft actually has more capability, better performance on almost every metric than traditional aircraft.
Okay, great.
Single pilot certified, Part 23 standards. We are planning that many of our customers will want a second pilot on board, either for just insurance or safety, but also because there's a pilot pipeline, and they got to have a fresh pipeline of pilots trained up, and so having that right seat available for a co-pilot is really important to a lot of our operators.
Now, you think there's going to be a cargo configuration also?
Oh, absolutely, yes. We have customers who fly passengers and cargo.
Great. Well, shucks, I've enjoyed this conversation. Anything else you'd like to add before we call it quits?
Well, I would just say that, Brian, it's a really exciting time to be in aviation. And if you're kind of used to the same old from the traditional aerospace vendors, there's a lot of new startups in this space, and it'll be very exciting to see where this all falls out. And I would think about it as, the first real revolution in aviation happened after the Wright brothers flew. The second one was really after the invention of the turbine engine, right? And the DC-8 and the 707 really opened up a whole world of travel. And now on the exact opposite end of the flight envelope, right, low and slow, is electric aviation. And that's going to open up a whole new set of possibilities that, much of the world isn't even really thinking about today, but is going to, I think, change the way we travel.
And being able to handle the shorter runways can hit most of those maybe less served areas with the 135 and maybe regionals and stuff. We go with that.
Do it with a quiet aircraft and a sustainable aircraft. That's all very important for the future.
Great.
Yeah.
Well, Marc, thank you very much for spending some time with me today. And once again, this is Brian Purdy with the Florida Aviation Network, live and in the clear from NBAA Convention 2023, Las Vegas. Have a great day.